All right, I'll start. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students, for another week. Almost done. Just pray to be with us today. Help us to glorify you, Lord, in what we do. In my prayer, Lord Jesus. Amen. All right. I need to start with this example because, well, the other the other poor section had me half do it, and I told them I'd put it at the start of today. So here it is. Then I'll go back and talk about the big picture and such. So start with an example here. Suppose you're faced with the limit. This is number 15 of section 11.6, I believe. We'll also do some 11.5 problems today, okay? Anyway, so 11.5 and 11.6 are both more or less on Lhopital's rule and limits at infinity and such. So here's a problem. X goes to 0 of 1 over sine squared x minus 1 over x squared. So the reason that this limit is indeterminate, it has type infinity minus infinity, right? And so infinity minus infinity, it's not 0, it's not even a number. It is merely an expression to indicate that that's the pattern of the limit, right? Because if we plug in 0, that's supposed to be 0. If we plug in 0 into sine, you get 0, and so sine squared is also 0. And of course, 0 going into x gives you 0, and same for x squared. So this is something very large minus something else very large, right? So we can make a common denominator, like so, and then we have something that has the form 0 over 0. That's what I need in order to apply Lhopital's rule, right? Lhopital's rule is for expressions of the type 0 over 0 or infinity over infinity. So probably try to zoom in on these, yeah. So we're to here. So we apply Lhopital's rule, which means I differentiate the top and I differentiate the bottom separately, right? Differentiating the top gives me 2x minus 2 sine x cosine x by the chain rule. On the other hand, the denominator, differentiate gives me 2x sine squared x, and then plus 2x squared sine x cosine x, again by the combination of the product rule and the chain rule and downstairs. Now at this point, this I recognize as being sine 2x, and I recognize that, the 2 included, being sine 2x. The reason I do that is because I realize I'm going to have to apply Lhopital's rule again. And so to not do this is to face yet more product rules. So it's in your best interest to simplify to sine 2x. All right, then we apply Lhopital's rule again. Upstairs, I get 2x differentiates to 2, sine 2x differentiates to, there's a minus here, minus 2 cosine x, cosine 2x by the chain rule. Downstairs, we have ourselves product rule on this gives me 2 sine squared x plus 4x sine x cosine x by the product rule just on that first term. Now I do the product. Now this, remember, I've simplified to x squared times sine x. So the derivative of x squared times sine x gives me 2x sine 2x, 2x sine 2x times plus x squared times 2 cosine 2x. Again, that's the product rule on x squared times sine 2x. Yeah? So then I'm like, well, I can simplify some of this because that's really collapsing that down. That's really just 4 sine 2x times x because, 2 sine x cosine x is sine 2x, right? So I got that here and here. I can combine these into one grand glorious 4x sine 2x term. Then I do Lhopital's rule again. So differentiating the top isn't too bad. That's 4 sine 2x, all right? Differentiating the bottom, well, I've got myself a 4 sine x cosine x. And then this gives me a product. Rather, this one gives me a product. Gives me 4 sine 2x plus 8 x cosine 2x by the chain rule. Then this differentiates to 4x because x squared is 2x. 2x times 2 is 4x. 4x cosine x minus 8x squared because I get 2. Why do I have an 8 there? Is that right? Not sure I believe in this 8. Derivative of cosine of 2x is minus 2 sine 2x. That's a 4. Again, it's type 0 over 0. All right? So then what? As long as it's type 0 over 0 or some indeterminate form, you don't give up. You keep trying. Well, I guess you can go up and try a different approach. You can go back to the start and try some different approach, but you're not done, right? You find 0 over 0, that just means that you're not done, all right? That means you have work to do. So one more step, we'll do it though. Differentiating this top gives me 8 cosine 2x. And then at this point, while I do love writing and differentiating, there's really no sense in, now that I've got something that's non-zero, there's hope, okay? So really all I need to do is collect the terms which can be non-zero down here. Any term which has sine 2x, or a naked x or x squared, is going to be 0 in the evaluation of the limit x going to 0. So it doesn't hurt me to not write down those terms in the calculation. So this plus dot 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 is stuff that goes to 0 as x goes to 0. Like this differentiates to, this differentiates to what? It differentiates to, well, that's just that. Let's see here. That's just that. This one though, there's also in principle a 8x times minus 2 sine 2x term, which I didn't write down because I don't need to, because that goes to 0, right? Similarly for this, there's also a minus 8x sine 2x term, which I didn't write down, and both of everything differentiated from here goes to, all of these either have an x or a sine 2x left in them under differentiation, so they go to 0. So this is all that matters for 8, 8, 4. Add those up, you get 24. Upstairs, you get 8. Cosine of 0 is 1. And so we get 8 over 24, which is 1/3. I'm happy to report that is the answer in the back of the book.
Sir?
Yes, sir.
You got 8 over 24,
8. 4 plus 8 is 12, plus 8 is 20, plus 4 is 24. Nothing too sneaky. And everything that I haven't written down is 0, because it's either got a sign or an x squared in it, multiplicatively. Obviously, that's a hard example, right? All right. I got stuck in the first section about right here because I inadvertently made this a 4, and then I got really confused. Because if that's a 4, then it made like something finite over 0, which would be infinity, right? But the answer is a 1/3, and I kind of trust the book, so I knew I did something wrong. Anyway, that's that. Let's look at a simpler example, all right? Tangent times the natural log of x, all right? So consider that. Let me erase this, if that's okay, because I don't want to distract you guys with that. Now that we've gotten it out of our system, let me tell you where we're going. So here's the deal. All of today is going to be L'Hopital's rule. I'm not going to prove the major theorem, not yet anyway, in section 11.5, the Cauchy mean value theorem. I should prove that for you guys, but I haven't yet. Maybe I'll do it Monday. But then Monday will be the day we talk about the homework from L'Hopital's rule, okay? So I want you guys to try the homework on L'Hopital's rules this weekend. And you can come ask questions about it Monday. Then come Tuesday, we'll go on, hopefully, to the remainder of chapter 11. And I may just end up just covering that material for the rest of the week. The homework, the next homework will be due Friday next week. So hopefully I can get something back to you by the Monday of the week after, and then we'll have the test on that Tuesday of the week before spring break. Hopefully I'll get the quiz back to you Monday. We'll see. And I'll try to have more quizzes next week as well. So. All right. Any questions about the plan? Okay. All right, so here we have a problem. Tangent times natural log. Tangent as x goes to 0 from the right, it's like tangent of 0, right? Which is what? Tangent of 0 is sine of 0 over cosine of 0, which is 0 over 1. Did you see me pick up a calculator to know that? I did not, and neither should you. If you have to pick up a calculator to calculate sine of 0, cosine of 0, sine of pi, cosine of pi, etc., 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 you are wasting your precious time. These things you should know by now. If you don't know them, stop and take a minute to learn them, because you'll save yourself an inordinate amount of time on tests as you go on. Not just in this class, but the next one, and the next one past that. Some of you are probably going to at least take through differential equations, right? And this stuff keeps mattering all the way through there. So it's in your best interest to become familiar with these familiar facts. Anyway, I digress. So I got two choices. I've got 0 times infinity, right? I can either bring natural log into the denominator, or I can bring tangent into the denominator, right? If I bring log into the denominator, I just have tangent of 1 over 1 over x. 1 over natural log of x, rather. This is weird. I don't know. I don't like that much. So I decided this was a better route. So what I do is natural log over 1 over tangent, right? Right? That's cotangent, right? So this is an important trick to know about. We can always take 0 times infinity and either convert it to 0 over 0 or infinity over infinity, depending on what's better to go with. I mean, which you should do in a given problem. I have no general advice. I just know that you should know about both of these options and keep an open mind to pursuing either route. Okay. So here I do natural log over cotangent. Now, let me just clean this up. So cotangent. All right, so that's infinity over infinity. See, log of a very small positive number is minus infinity. Cotangent of a very small positive number is also, I think it's plus infinity, if I remember right. Yeah. It doesn't really matter, guys. So just to go back here, I tried to just state the general Lhopital's rule over here, just for our reference. Either we have going to 0, type 0 over 0, or you can have plus or minus infinity, and it really, these pluses and minuses don't have to be tied together. One could go to infinity, the other one could go to minus infinity, or vice versa. It doesn't matter. Either of those, all those cases we think of as quote-unquote infinity over infinity. In all those cases, we have this Lhopital's rule, which says the limit of the quotient is the limit of the quotient of the derivatives, differentiating the numerator and denominator separately. I haven't really even attempted to explain to you intuitively why that's true. We've just been accepting that as some sort of magical fact in here and working with it. I will at some point get back to the topic of why is this intuitively true. I just put that at the end of the discussion rather than the start. Maybe that's wrong. Anyway, so getting back to the problem at hand. This, by the way, is which number in the homework? That's actually number 12 from section 11.6. Phew, I didn't assign it. Okay. This is number 12 in section 11.6. Okay. All right. So, Lhopital's rule. Derivative of natural log, 1 over x. Derivative of cotangent, minus cosecant squared. Agree? All right. Then I clean it up. So that's sine squared upstairs and minus x downstairs. I definitely want, I want to have an x, because I know when I apply Lhopital's rule another time, that just goes away. So it's definitely better to have x appear rather than 1 over x appear, ultimately speaking. So that's why algebra, it's a combination, right, of L'Hopital's rule and algebraic steps, right? When we talk about using L'Hopital's rule, we're not just talking about using L'Hopital's rule, we're talking about algebra and L'Hopital's rule. It's always that. And every last stupid thing you forgot about differentiation from Calculus 1, it will come and exact a price from you here, right? If there's a hole in your armor, an arrow will find its way through, pierce your flesh, and points will flow out. Sorry to be so violent. All right, anyway, so that's where we got to. Now, again, 0 over 0. Apply L'Hopital's rule. I get 2 sine x cosine x. Differentiation of minus x is minus 1. Well, that's nice. Hey, so it's 0. Once we finally get to something which has the form, number over 0 or 0 over number, well, if it's number over 0, that's not indeterminate. That just blows up. All right? If it's 0 over a number, well, that's 0. That's the type. Any questions about this example? Okay. I will come back to the green. That's an extension of this example for later, but first I want to talk about some more. We'll talk about the... What have I done? Oh, okay. We'll talk about the indeterminate powers. I think this room is about to blow up. It's unstable. Things keep falling off desks. Maybe it's your nervous excitement about L'Hopital's rule. That's what it is. Let's see here. So I understand. It is pretty awesome. So number 9 in section what? Oh, where are we? Number 9 in section 11.5. Now, some of these 11.5 problems could be solved without L'Hopital's rule. This might be one of those, but I don't mind using L'Hopital's rule here. As x goes to 1, we're looking at the square root of x minus the 4th root of x over x minus 1. Bless you. And so that's 0 over 0. So it's type 0 over 0. I can apply L'Hopital's rule. Doing that gives me 1/2 x to the minus 1/2 minus 1/4 x to the minus 3/4. And then derivative of x minus 1 is just 1. Right? This would have been a kinder problem to start with, right? But I had to talk about that stupid number 15 to get it out of the way. I'm sorry, you guys. Well, you guys generally have a better lecture in here. We can sacrifice a little bit to make up for what I did to the earlier section, right? It seems fair. All right. Anyway, so that's when you plug in 1, that's 1/2, and that's 4th, right? Because 1 to the minus 1/2 power is what? Yeah, if you need to pick up a calculator, figure that out. Not a good thing. 1 to the minus 3/4 power, again, no calculator needed. 1. 1/2 minus 1/4 is a 4th. Because if we divide a number by 1, again, I hope you're not picking up the calculator to calculate that. I think you hear a theme here. 1/4. So here's number 9. Any questions? All right, so I don't want to mislead you. Not every limit is done with L'Hopital's rule. Some just require algebra. Here's one. If I look at the limit as x goes to infinity, let's say, of e to the minus 3x, e to the minus x times 3 to the 2x. All right, I could look at that. Now this has type what? This is type 0 times infinity. All right, type 0 times infinity. So it's indeterminate, right? But L'Hopital's rule really won't help you out here. I mean, you can do L'Hopital's if you want, but it kind of takes you nowhere pretty fast. So this is 3 to the 2x, right? Divided by e to the x by algebra, right? What happens if I apply L'Hopital's rule? What is that something? 2, yeah, 2 times what? No. This is not a power function. This is an exponential function. It's natural log of 3 times 3 to the 2x is what we'd have upstairs. And then downstairs you have e to the x. But as you can see, all we've really done is taken the one we started with and multiplied it by a number, 2 natural log of 3. And if you apply L'Hopital's rule again, you know what'll happen? You just get another copy of 2 ln of 3, and it just keeps, it goes nowhere. I mean, or it goes, it's like, I don't know, it's like trying to go somewhere by staying at a bus stop. I don't know. It doesn't work. So, unless you get on a bus, right? I don't know. Let's see here. So this, actually, what we can do is use our old friend algebra. This is 3 squared to the x over e to the x. So you can rewrite this as the limit as x goes to infinity of 9 over e to the x power. Is 9 over e smaller than 1 or larger than 1? So what happens if we take a number larger than 1, raise it to the infinite power? It goes to infinity, right? So as you can see, L'Hopital's rule here is wholly unnecessary. And in fact, it's useless to us here, right? All right. There's something I should talk about before I forget. Why are we doing this? I'm not talking about the intuition of L'Hopital's rule just yet. I'll talk about that later. But, we were talking about sequences, right? Sequential limits. Why are we talking about L'Hopital's rule all of a sudden? Now we're talking about these, functions of x. We were talking about functions of n before, right? Where n was a counting number, 1, 2, 3, 4, natural number, right? The thing is, there's a connection between these two worlds. That connection is this beloved continuous extension theorem. So I called it a remark earlier, but really it's a theorem. Theorem. Let me put a bubble around it. Okay. So basically, if you have a function f of x, all right, and it matches f of n. See, and I really should have a qualifier here. For which n? For all n in the natural numbers. And, oh yes. Sorry, and yeah, I also need, for all x in the natural numbers. I don't know, it's stupid notation. X equals to n in the natural numbers. All right. In other words, I'm trying to say that maybe more to the point, f of n is equal to a sub n is really the thing, all right? Where f of x is defined for x being any real number, all right? Suppose f is continuous from 1 to infinity in particular, all right? So graphically, it's something like, here's the function, right, f. So the picture of the sequence, of course, is just doop, 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 and so forth and so forth and so forth. The point is, the function matches the limit. Now, I guess in principle, a continuous extension of that limit could have all kinds of weird junk in it. Like there could be one of these guys, wee, like that. It would still be a continuous extension of the sequence, or you could have could have like this, right? Or you could have like over here. Sorry, I'm getting carried away with this. Those are supposed to satisfy vertical line test. I mean, there's infinitely many continuous extensions of a given sequence, all right? You can do all kinds of crazy stuff between the sequence points. But if the limit of the function exists as x goes to infinity, all this kind of chicanery gets washed out in the limiting process. And so whatever limit the function f possesses, the same limiting behavior must be possessed by the sequence which it continuously extends. And that's the continuous extension theorem, is that if your function matches a sequence at natural numbers, then the limit of the function will be the limit of the corresponding sequence. And it's greedier than that still. It's also true in the infinite case and the minus infinite case as well. Like here, as an application of this, from this calculation, I can immediately conclude that the sequential limit as n goes to infinity, of e to the minus n times 3 to the 2n is equal to infinity by the continuous extension theorem. And I don't really get anything from this one, right? That one's just kind of like a pure Lhopital example. This one doesn't really tell me much. Well, just for you guys, do you know the connection between limits at 0 and limits at infinity? Fun fact, limit as x goes to 0 from the right of, say, g of x is equal to what? The limit as t goes to infinity of what? Not g of t. G of 1 over t, right? Yep.
The continuous extension theorem,
Mm-hmm.
can it be both ways or just one way?
Just one way. Because, well, I don't know. That's a good question. Is the converse is true as well? I don't know. I have to stop and think about that. I'll think about that. That's an interesting question. I mean, I would have to add the assumption that basically the theorem that you're suggesting is given a sequence, and let's keep it concrete. Let's say a sequence, let's look at just the convergent case. The question I think you're asking is, given that the limit as n goes to infinity of a sub n is equal to L, right? Is it possible to construct a function f continuous from 1 to infinity which restricts to the sequence at whole numbers and also has limit L? If I drop the continuous, I can do it already. What I would do, so here's what I would do. If you drop the continuous, my function, I would just do this. That's the laziest thing I can think of right off the top of my head. So this function will definitely have, it's defined from 1 to infinity. It definitely has the same limiting behavior. Oh, I know what to do. Just connect the dots. So I think the converse is true if you just connect the dots. I bet you can prove that that's definitely going to be continuous and have the same limiting value. So I think you're right. I think there is a converse as well. Mm-hmm. Oh, I'm sorry. I was going to think about that later. Sorry, you'll forgive me. If you ask an interesting question, I might have to think about it. So this, if you know this, like we can bogart this example for another one. I mean, that's not the right, I'm sorry, I'm incorrectly using bogart. Let's see here. We can twist this example, let's say. And so the limit as t goes to infinity of what? Limit as t goes to infinity of like ln of 1 over t over the cotangent of 1 over t is equal to 0. If you remember that little theorem about the exchange between limits at infinity and limits at 0. Fun fact. And then the continuous extension theorem would tell us the limit as n goes to infinity of the natural log of 1 over n of the cotangent of 1 over n is equal to 0. By continuous extension theorem, you know. All right. Any questions? Okay. Oh, yeah.
So in that case, if it's two things multiplied by each other, you return that to making it, like the first step would be making it to a quotient.
Yes.
Of the two products.
Right. Unless of course, I mean, it wasn't strictly speaking necessary to make this into a quotient, right? Like if you know your algebra well enough, you could have gone directly from here to here or something like that. You could even rewrite this, right? There's another way we could have done that problem. For example, you could also do this, which would be useful to know about. E to the minus x times e to the ln of 3 to the 2x would have been e to the minus x times e to the 2x ln of 3, which would be e to the 2 ln of 3 minus 1 times x. You could do that. No quotients there. Just our knowledge of exponentials and logs and how to convert from base 3 to base e. And then you look at it and go, well, 2 times the natural log of 3 minus 1 is a positive number. Now there I probably would need a calculator. Sorry. But maybe some of you don't. I guess I wouldn't if I thought about it for a second. But anyway, that's e to a positive number. So if I take x going to infinity, I've got like e to a positive infinity, which is infinity. That's another way we could have looked at it. But certainly, yeah, quotients are important, but they're not the only game in town. They're the biggest game for what we're doing. All right, so that brings us to our next sort of topic. Well, not sort of topic, just topic. I say sort of too much. Let's see here. And so let me go through this example here. This is number 27 and 11.6. I'll go through this one, I'll go through that one, then I'll try to do one more for you guys. So if we look at the limit as x goes to infinity of x cubed plus 1 to the 1 over natural log of x, this is a new thing. It's not infinity and minus infinity, it's not 0 times infinity, it's just something different, right? This is type what? This goes to infinity. This thing is like 1 over infinity. This fraction is going to 0. So this is type 0, infinity to the 0, which is one of our indeterminate powers. All right? So the way to deal with that is to use a dirty trick. The dirty trick that we use, of course, I'm a Cruz supporter, so I like this. It's such nonsense. Exponential of the log of this, right? Now, I can do that without changing the expression because I need to know that what I'm doing that to is positive, right? Is x cubed plus 1 to the 1 over natural log of x a positive quantity for x greater than 0? Yeah, for sure it is. So I can do this. And then that entitles me to the rights and privileges thereof, in particular, properties of logs. So I can pull the 1 over n, 1 over natural log, out of the log by one of the properties of the logarithm, right? ln of a to the p is p times ln of a, right? Assuming a is positive. So I bring ln of x out. But exponential is it's a pretty nice function. It's continuous everywhere. So that means I can bring the limit inside the exponential by the composite limit law. So I bring the limit inside the exponential. And then I give this a name. I call this star. Right? So I've replaced the problem I have with an equivalent limit of something that doesn't involve a power. It just involves natural log of x cubed plus 1 divided by natural log of x. Right? I got to figure this out. All right? I, at this point, say, okay, I got to figure that out. I'm going to give it a name. I'm going to call it star. And then I'm going to go off and I'm going to solve it separately. So that's what I do over here. Okay, so this is star. So star is the limit of log of x cubed plus 1 divided by log x. And I told my earlier section that I lose about 30% of Math 126 here by making this step, because they are not aware of the fact that 1 over a times b, you laugh, but this is a significant thing to not know. It will stop you in your tracks. Many points have bled out of this gaping flesh wound in your mind. So right here, we have 1 over a times b is b over a. So this is like the fraction times that. I can rewrite it as a quotient of log of x cubed plus 1 divided by log x. All right, enough about that. Any questions so far? Where did the natural log come from? Where did it go? Oh, Lhopital's rule. So we differentiate the... See, right there. Is a Lhopital. So Lhopital's rule, this is infinity, type infinity, that's type infinity, because logs of huge numbers are huge. And so chain rule, 3x squared divided by x cubed plus 1. Derivative of natural log, 1 over x. At this point, I no longer need Lhopital's rule. What I need is to do algebra. So algebra brings the x upstairs, gives me a 3x cubed. Algebra brings this reciprocal of the numerator to the reciprocal of the total expression, just x cubed plus 1, like so. Now, I could do Lhopital until I could like Lhopital this to death until it's like a number, but it's just easier to just use algebra, right? So divide the top and the bottom by x cubed. That gives me 3 over 1 plus x cubed. As x goes to infinity, 1 over x cubed goes to 0. Consequently, the limit is 3. Now that is not the problem we were working, right? This is something we need to work out to solve the problem we were working, which was this one. We have now figured out that star is 3. Therefore, the answer, the limit as x goes to infinity of x cubed plus 1 to the 1 over natural log of x power, is e to the 3. Yes, sir.
So are you saying that would be considered side work?
Yeah, I mean, that needs to be included in the solution, but I wouldn't try to do it in one grand glorious calculation. I would do is like give it a label, work it out below or to the side, and then put it in. I don't try to do it in one uninterrupted calculation. Anyway, that's my way of expressing it. And I almost always call this thing star. That's just my stupid habit. I'll stick with it, though. All right, so this is how we do all the indeterminate powers. It's the same. Was it answering me? Yeah. So any indeterminate power, we can use this same technique to do. Here's another one. If I was looking at the limit as x goes to 0 of x to the tangent x, What do? I take this, put an exponential and a log in. I pull the limit out. I skip the step now, you see? So I just went ahead and put the limit inside the exponential. I have exponential, the natural log of that. But then the power, the properties of log brings down the tangent. Then I've got exponential, the limit as x goes to 0 from the right of tangent natural log. But, hey, I just worked that out, and it's 0. So this is e to the 0, which is 1. Let's work another. I think we're in 11.6 more or less here. I'm trying not to do your homework. You're like, don't try so hard. You're fine if I do? What's that?
So, like, an exponential thing is always continuous without fails.
Yep. As far as I know. I mean, I'm not sure I can even think of another number system where the exponential is discontinuous in some natural way. It's definitely continuous for the reals and for the complexes, which are just about all you'll see in coursework. Here's one. By the way, we had, let's see, this was, I guess this was actually type what? 0 to the 0, wasn't it? So we've seen infinity to the 0, we've seen 0 to the 0. Oh, this is another 0 to the 0. How boring. Fine. This is the exponential of the limit as x goes to 0 from the right of the natural log of x to the sine x power. Hope you don't mind I brought the limit inside. I could write another step, but I just get tired of writing that step. In fact, once I really understand this, I go straight to what I'm about to write. So like on the next test, I would probably be cool with you going straight to here as long as you understand what you're doing. I mean, frankly, if you go from this to this, that indicates to me that you've studied and you have a command of the material. Because the writing we do in between that point and that point is the same every time. But I mean, technically speaking, the complete argument involves those other steps, of course, but then what? I call this thing star, right? I think as a general rule, leave natural log where you find it. I can't remember a problem where like flipping the natural log was helpful. What do you say, cosecant? So we have infinity over infinity, I believe. Because cosecant's 1 over sine, which of course is infinity as x approaches 0 from the right. So I get 1 over x divided by minus cosecant cotangent, right? This is actually, well, of all the embarrassing things, this would have been easier if I'd flipped the natural log. No, I'm wrong, because it still would give me a natural log. I'm not thinking correctly. I would still have 1 over natural log, and there'd still be a natural log in it, and that would be no, it's not good. This is fine. This is, take our medicine. What is this? Sorry, let me just work instead of worrying about how not to work. This is what? Put it in terms of sines and cosines. What is that? So it's like 1 over sine, right? Cosine over sine. So this is really like sine squared x over x times, I gotta put a minus somewhere in here, minus x cosine x, yeah. Lhopital, right? 0 over 0. Wonder if I could invent a problem that forced you to go through all the different indeterminate forms in one foul example. It's okay if I don't? You guys are no fun. No one ever encourages me towards making more interesting test problems. It's a weird thing, isn't it? Now, look here. This is what? You can plug in the x equal to 0. You get 0 over minus 1 plus 0, also known as 0. So this is, so this time type 0 to the 0, right, works out to 1. That time type 0 to the 0 works out to 1. Oh no, giving you guys the wrong impression. Yeah.
Instead of doing all that trick stuff on the side, you could just put like cosecant and cotangent in the numerator. And just like flip it so it would be like sine x tangent x, and then take the derivative of both.
Oh yeah, I like that. So you're saying instead look at it as limit as x goes to 0 from the right of, yeah, very nice, very nice. Like tangent sine x, like that.
Yeah, over.
Yeah, absolutely. That'd have been smart. Cool. Absolutely. Yeah. Not bad idea at all. In fact, that's kind of a useful algebraic shortcut, right? Tangent in the denominator becomes cotangent in the numerator and vice versa. Like the co-functions, when you reciprocate them, become the functions. Aw. I felt like we just started today, and now we have to go to part ways. It's sad. But I'll see you again. Just a few, 72 hours, is it? I don't know. Yeah. Have a good weekend, you guys.